What's up, my guys, gals, and non-binary pals? Welcome to our first class of Unit 2. So in Unit 1, we focused on equations, which establish a unique relationship, in this case, sameness or equality, between two expressions. But if we think about it logically, if we randomly take any two things out in the real world, it is way more likely that they're going to be different than that they're going to be the same. So in math, we need a way to talk about those relationships too. Remember, by definition, we defined an equation as a mathematical sentence with two or more equal expressions. Our guiding question for today then is, well, what happens if they're not equal? Which necessarily leads us to Unit 2, where we're going to take the principles of solving equations we learned back in Unit 1 and apply them to solving some linear inequalities. So the title of our lesson today, let's get introduced to these inequalities. Class 1, Unit 2. So an inequality, by definition, right? An equation establishes sameness, equality. An inequality, instead of thinking about them being the same, I want to find a slightly different word for that. The word that we're going to use for what an inequality does, rather than saying that these two things are the same, it's going to compare them and make a judgment about their relative size. So by definition, we'll say that compared to an equation, an inequality is still going to be a mathematical sentence. It still contains some punctuation marks. But instead of equating two things, it's going to compare them. So it compares two or more, right? Once again, like an equation, I can have multiple inequalities wrapped into one. It compares two or more expressions. Just like an equal sign establishes a specific relationship, we have four different symbols in math that can establish some comparisons. Take a second and think to yourself, do you remember what your four inequality symbols are? Take 5 seconds, pause the video. What do you think? 5, 4, 3, 2, 1, and stop. So I want my four inequality symbols. Hopefully you can remember that they are our greater than symbol, which is represented here by something like, I often think of the alligator mouth. It opens up to the right. We've got our less than symbol, which opens up in the other direction. And then I also could establish, well, if I have a greater than, I could also be greater than or equal to and less than or equal to. So again, our four, we've got our greater than, our less than, our greater than or equal to, and our less than or equal to. However, in math, we won't always encounter this exact language. Much like we did with equations, I'll often want to do some translations. So there are a couple of different ways that I can write or indicate that I'm working with some of these symbols. Take 10 seconds, think to yourself, what are some other ways that you could express in words the concept of something being greater than or larger than something else? Same thing with less than, greater than or equal to, less than or equal to. See what you come up with. I'm not necessarily expecting you to get it, but what are some different ways that you could maybe express this concept? Go ahead, play around, see what you come up with, and we'll chat. Okay, well, for something like greater than, some other ways that I can refer to greater than in the context of a problem, well, one translation that you might see, I could say more than. I could also say if something's greater, I could say it's bigger, it's more. So greater, more, bigger, all interchangeable. Less than, similarly, the opposite of more is less. The opposite of greater, I could say something is fewer than. I could also say something like it's smaller than. If I'm thinking greater than or equal to, well, if I'm thinking about that, I could be greater, I could be equal, but that means that I can't be less. So if I can't be less than, then there are two ways to say that I can't be less than. One way to say that is I am at least. So greater than or equal to, if I'm at least something, that means I have to be bigger than or exactly at that. I can't go below it. Another way to say that, if I'm at least, I could say I am no less than. Right? If I'm greater than or equal to, I could be greater, I could be equal, but I can't be less than. Similarly, same idea for less than or equal to. If at least gives me greater than or equal to, then at most would be my equivalent for less than or equal to, right? If I'm less than or equal to, that's my cap, my upper limit. So my most value would be my at most. And same idea, if I'm no less than, then my equivalent there would be that I am no greater than, right? I could be less than, I could be equal to, but I cannot be greater than. Fantastic. With that in mind, I've given you 3 inequalities here that I'd like you to fill in using a symbol, comparing -3 and 3, comparing -5 and -8, comparing 1/3 and 2/5. Pick one of your inequality symbols here that when you plug it in, slot it in, fill in that blank, will happen to make this statement true. Take 10 seconds, see what you think. Go ahead. And stop. So I've got -3 and 3. In this case, I just want to fill it in with an inequality symbol that makes it true. Well, which one is bigger? In this case, it's the -3. No, of course not. It's the +3. So a positive number will always be larger than. So my two options could be either, in this case, less than, because -3 reading from left to right is less than the 3. So I often think, if you're thinking like your alligator mouth, the alligator mouth wants to get more food. It wants to feed itself. Think back to your Florida man. That Florida man can't ride his alligator if that alligator ain't well fed. So in this case, we want to eat the thing that's going to give us more. So you could write greater than, or you could write greater than or equal to. -5 and -8. In this case, the temptation might be to say that the -8 is bigger because 8 is larger than 5. But if you think about where they live on the number line, -5 is actually to the right of -8. So this guy happens to be the bigger one. So I could use either my greater than or my greater than or equal to symbol. And then for 1/3 and 2/5, well, if I want to compare these two things, what do I need? Remind me, take 5 seconds. What do I need to compare these two fractions? Go, 5, 4, 3, 2, 17, and stop. Well, if I want to compare 1/3 and 2/5, I'm not totally sure about how big they are unless they've got the same denominator. So 1/3 and 2/5, what's my least common denominator between these two? Very good, invisible person. I can take a common denominator of 15. Well, how many 15ths is 3? To get from 3 to 15, I need to multiply by 5. So if I have 1/3, that's the same as 5 15ths. 2/5, to get from 5 to 15, I multiply by 3. So that's equivalent to 6 15ths. And here, 6 15ths is bigger than 5 15ths. So my alligator mouth will open to the right. So I could do either my less than symbol, 1/3 is less than, or equal to 2/5. Fantastic. From here, let's say that I want to do some translations. Remember that math is predicated on our ability to take words and turn them into symbols. So let's take each of these number sentences here. I want to translate them into inequality statements. The difference of a number in 16 is at most 30. 9 is greater than 3/4 of a number. So like we did back with equations, look at each of these sentences. What words immediately cue you into particular operations, to particular inequality symbols, and with that in mind, can you build an inequality that represents this sentence? Take 30 seconds, play around, see what you come up with, and then we'll chat. Alrighty, I'm feeling chatty. The difference, so difference, remember, that immediately cues me into the operation of subtraction. So the difference of a number, so I don't know what that number is. In this case, let's make it a variable. So my number, maybe I'll call it n. The difference gives me subtraction. The thing that I'm finding the difference with is that 16. So our n minus 16. And then is at most, well, at most, remind me, what inequality symbol does that translate to? Well, if it's at most, that means I could be less than, I could be equal to, but I can't go above it. So I'm at a less than or equal to 30. So there's our translated sentence. N minus 16 is less than or equal to 30. Same idea here. 9, in this case, well, that's 9, is greater than, of course, can be represented here using our alligator mouth opening to the left. And then I've got 3/4 of a number. Well, 3/4 I can write as 3 over 4. Of course, always gives me which operation? When it's by itself, of gives me, very good, multiplication. So I could write my multiplication with a dot, or in this case, I'm actually just not going to bother writing it, because again, multiplication can also be expressed using just sandwiching two things together. In this case, I'm sandwiching it, words, with a number. That number I'll represent with n. Beautiful. So 9 is greater than 3/4 n. Cool. There's your idea. Here's 3 more to play around with. I'm not going to read them to you. I'm lazy. Take 30 seconds. Take a minute. Take as long as you need. Pause the video. Let's find some words that translate nicely into symbols. See if you can translate these into some inequality statements. Go ahead. Take a second. And then we will come back together. Are you done? Let's do it. 0 is fewer than twice a number plus 1. Well, taking it piece by piece, I have a 0. I've got is fewer than. I've got twice my number. And then plus my 1. So 0, of course, is 0. Fewer than, well, that's another way to write less than. Twice a number, we should hopefully remember from all those consecutive number problems we did. Well, twice a number, that's 2n, whatever that number is. Plus, of course, gives me my addition. And there's 1. So 0 is less than 2n plus 1. 10 is no more than, there's my inequality, the sum, that gives me some kind of operation, of 3 times a number and 4. So 10, I can immediately jot that down. Let's move from left to right. No more than, again, don't fall into the trap. You seem no more, so that might make you think that we're working with a greater than. But if I am no more than, I can't be more than. So I could be less than, or I could be equal to. So there's my less than or equal to. The sum, so there's addition for sum. 3 times a number, well, once again, just like twice a number, 3 times a number would be 3 times n and 4. So the sum of 3n and 4, in this case 10, is going to be less than or equal to that 3n plus 4. And same idea, -7 divided by, in blue for consistency 10, is at least twice a number minus 5. So from here, -7 is, of course, just -7. I'm going to divide that by 10. So I'm going to choose to write that as a fraction. If you want to write that using a division symbol, be my guest. Is at least, so at least, again, if I'm at least this, then I've got to be at minimum that or bigger. So I have to be greater than or equal to. Twice a number, well, there's our 2n minus 5. Fantastic. In a couple classes, we'll think about, well, how do I actually go about solving this inequality? But for now, as long as I can translate back and forth, I'm satisfied.